Okay, in this video we're going to talk about projections. Okay, so define the projection of one vector onto another vector in an inner product space by the projection is inner product of u with v divided by the inner product of v with v, all multiplied by the number or the vector v. Notice this is exactly the same definition for projections that we had for r to the n, only instead of using a dot product in the numerator and denominator, we're using the inner product. Again, no surprise. The entire point of inner products is just other things that look like dot products look like on r to the n. So I'm going to try an example, actually try and calculate the projection of x squared onto x using the same inner product I've been using the last couple of videos. So in order to do this, I'm going to need to find the inner products. Let's see, f onto g, so we need f with g, and then the one on bottom is going to be the one on the bottom, so we're going to need inner product of g with itself. So right off the bat, we know we're going to need to calculate inner product of f with g and inner product of g with g. And I'll just go ahead and calculate those out. So we have the definite integral of x squared times x. Integral of x cubed would be 1/4 x to the 4th from 0 to 1, which would be 1/4. Okay. Inner product of g with g would be x times x dx, which is x squared. Integral of x squared would be 1/3 x cubed from 0 to 1, which would be 1/3. And so the projection of f onto g should be the inner product of f with g divided by the inner product of g with g multiplied by g. Okay, so we know the two numbers. Again, the inner product, like the dot product, spits out a number, so my numerator and denominator should be two numbers. We have 1/4 divided by 1/3 multiplied by g, which in this case is the function of x. And let's see, what is this? This is 3/4 x. Okay, something to point out, the projection of one vector onto a second vector is always going to be parallel to the second vector, so we're always expecting to get a multiple of the vector on bottom, which hopefully isn't surprising if we have a fraction, which is a number divided by number times exactly that vector, or exactly that function in this case. Okay, so this is how we would find a projection of one function onto another. Okay. If we're going to talk about projections, there was one other thing we mentioned in the same section as projections when we did talk about the dot product, and that was our good old friend Gram-Schmidt. So let's just talk about Gram-Schmidt and how it's different, how it's exactly the same. Given a basis of an inner product space, we're going to define the first vector of our orthogonal basis is the same as the starting vector. The second vector is the second vector minus the projection of the second vector onto what you already got. So if you take away the part that's parallel, what's going to be left is going to be perpendicular. So the projection is always parallel to the thing you're projecting onto. If you subtract the projection, it should be orthogonal or perpendicular. Okay, our third vector is going to be the third vector in the set, which is v3, and then we have to take away our projection onto both of the two that we already calculated. Okay, and then just keep going. So the first time we don't have to subtract any projections, then subtract 1, then subtract 2, and just keep going like that until you're subtracting a bunch of projections. When you're all done, you should be guaranteed that all these w's are orthogonal to each other. Their angle with each other is 90 degrees. Okay, if I wanted an orthonormal set, orthonormal just means our length is also 1, and so each of the w's, we would divide it by its length. Again, the length being the inner product. So if I stare at what's written on this sheet, I could have crossed out the word inner product. Just let this be a basis of v. Yeah, maybe shouldn't have crossed out v. Anyway, this is exactly the same whether we're talking about the dot product or the inner product. The only thing that's going to be different is how exactly do you calculate the projection. Is it a dot product over a dot product, or is it an inner product over an inner product? But again, it's essentially the same formula. And same thing here. How we calculate our length is going to be slightly different when we talk about an inner product versus a dot product, but it's still essentially the same, square root of the dot product or square root of the inner product. So I'm not going to run through an example all the way through of Gram-Schmidt, but it should be really similar to the Gram-Schmidt examples we've already seen. We just have to be really careful, maybe go back and brush up on projections and lengths in inner product spaces, because they're going to look a little funky that we're taking square roots of definite integrals and that kinds of things.